Hi, my name is Kunal Marwaha. I'm a graduate student at University of Chicago, and today I'll be talking about QMA and proofs without relative phase. This is joint work with Roozbeh and my advisor Bill. You can also see our talk at the Simons Institute from last July or the preprint on arXiv. So the context for this work is about the complexity class QMA and a related complexity class called QMA2. Now, the difference between these two classes has to do with entanglement. Both of them verify computation with a quantum computer, but in QMA2, you're given extra information about the structure of entanglement. Now, what we'd like to know is how different these two classes are. In a way, it's a complexity theorist's view of studying entanglement. So QMA is a set of decision problems. It's going to be a set that each decision problem is going to be associated with some verifier that runs in polynomial time on a quantum computer. And if the answer to the problem is yes, then there's some quantum witness, which we'll denote by psi, that makes the verifier accept with at least probability C. However, if the answer to the problem is no, then no matter what witness is sent, no matter what psi is given, the verifier will only accept with probability at most S. Now, in general, these are families of problems, one for every input size, and the input size is denoted n, and so both C and S can be functions of n. You can think about QMA as kind of the canonical quantum version of NP. Now, QMA2 is very similar. It's again a set of decision problems, each with a verifier. But in the yes and no case, the quantum witness must have this separability property. You can imagine that there are two quantum witnesses, psi1 and psi2, that are completely unentangled. In the yes case, there's some psi1 tensor psi2 that makes the verifier accept with probability at least C. And in the no case, no matter what pair psi1 tensor psi2 I'm given, the verifier can only accept with the probability at most S. Now notice that every problem in QMA is also in QMA2. How can I do that? If the verifier ignores psi2 and just looks at psi1, then it can run every protocol that was in QMA, just using psi1 as the witness. However, it's not clear how much more powerful QMA2 is. And that's kind of the setup to this work. I can tell you some things we know about QMA and QMA2. First, there's this phenomenon called gap amplification. So C minus S is often known as the promise gap in problems like this. And as long as C minus S is bigger than some inverse polynomial in N, then the gap can be boosted to 1 minus something very small, usually like 1 minus inverse exponential in N. For QMA, one technique you can use is called parallel repetition. This means that you run the protocol many times. In the yes case, the success rate of the protocol will concentrate around C. And in the no case, the success rate of the protocol will concentrate at most around S. And you can distinguish these two. For QMA2, you have to use an additional primitive called the product test by Harrow and Montanaro. And this allows you to kind of repeat the protocol, but still preserving this separability condition, or this unentanglement. We might also wonder about upper bounds. Now, all verification classes for quantum computers are going to be in NX. Why? The verifier runs in a polynomial time quantum computer, and that can be simulated in exponential time. Additionally, the witness, the quantum witness, can be simulated with non-determinism, hence the n. So both QMA and QMA2 are in NX. For QMA, we can do better. We can write down a semi-definite program to find, the value of the best witness, the acceptance probability of the best witness. And this program is in p-space. And in fact, we can do even better using, smarter techniques. But for QMA2, we actually have no other upper bounds besides NX. And this is not for a lack of trying. There have been many approaches to try to upper bound QMA2, but none have worked. And recently, I think people wonder that maybe QMA2 is in fact equal to NX. That's the reason we can't do any better. But that would be pretty surprising. That simple change in the definition gives a lot more power to the complexity class. So recently there was one new approach to study QMA2 that involves another set of complexity classes, QMA plus and QMA2 plus. So QMA plus again is a complexity class, so it contains a set of decision problems that have a verifier. But in the yes and no case, we're going to demand that the witnesses have non-negative amplitudes. So this means that, let's say in the computational basis, all the amplitudes of psi are real and at least 0. So in the yes case, the witness that makes M accept with probability at least C must have this property. And in the no case, we're going to look over quantum witnesses that have this property. And none of them should make M accept with probability more than S. We can also imagine this definition for QMA2+, where again we have psi1 tensor psi2, but they both have non-negative amplitudes. Now, it's actually not clear if these plus classes are more or less powerful than the non-plus classes. For example, the yes case is now more restrictive. So there are perhaps fewer problems that fit this requirement that the witness must have this non-negative amplitudes property. But in the no case, it's less restrictive. We only have to protect against psi1 tensor psi2 with non-negative amplitudes, not all psi1 tensor psi2. So does the plus add or remove power? Now, we could instead just require the restriction to non-negative amplitudes only in the yes case. This should only make the class weaker. But it turns out this class had already been studied, and in fact it's equal to QMA or QMA2, depending on if you have the two. So since the yes case, the change in the yes case makes no difference, changing the no case is going to make the class more powerful. So QMA is going to be contained in QMA plus, and QMA2 is contained in QMA2 plus. We can also describe some things we know about QMA plus and QMA2 plus. First of all, we might wonder about gap amplification. Now, the naive technique of parallel repetition doesn't work. And this is the first thing one would try if you're wondering if promise gap can be amplified. If you try running the protocol many times, and you take a partial measurement, you may no longer have this plus property of the quantum witness. So in the beginning, you might have plus all across, non-negative amplitudes across all the whole state. When you do a partial measurement, you might now have complex phases. And so it's not that these classes don't have gap amplification. We don't know that. But the simple technique of parallel repetition won't work. We might also wonder about upper bounds. Again, these classes are in NX. But the standard technique of upper bounding these quantum verification classes using a semi-definite program doesn't work. Why doesn't it work? Is because this plus condition is related to a notion of copositive programming. So if you write down the semi-definite program, then these problems, at least at polynomial size, can compute independence numbers of graphs and other things that are NP hard. And so at the exponential size, it could be as hard as nx. So this doesn't give you a technique to upper bound these classes. Now you might be wondering, okay, these classes are really weird. What's the point? They might be way too powerful compared to the regular QMA and QMA2. But actually, every quantum state is pretty close to a non-negative amplitude state. In fact, it has a quarter overlap. How do you see this? Take a quantum state and separate it into real and imaginary parts. Pick the ones that's bigger. Let's say it's the real part. Now, take that state and separate the positive and negative components. Take the one that's bigger. Let's say it's the positive state. Now, that state has non-negative amplitudes, or at least is a small transformation from having non-negative amplitudes. But it has a quarter overlap with the original state. And so this implies that for large enough promise gap, QMA plus can be simulated by QMA, and QMA2 plus simulated by QMA2. And so there are constants, C prime and S prime, where the classes are equal. Okay, so the plus isn't giving you that much power when the promise gaps are big enough. But the reason this class was introduced is because of something else that's really weird. For some other constants, C and S, QMA2 plus is equal to nx. And so on the one hand, it's equal to QMA2, but on the other hand, it's equal to nx, depending on the choices of these constants. And this gives you a new way to understand QMA2. If this QMA2 plus had gap amplification, if the promise gap could be arbitrarily amplified or boosted, then it would say that both of these classes are equal. QMA2 is actually equal to nx. And that would resolve a really challenging question about this complexity class QMA2. And I think this came as a surprise because this gives a new technique to study QMA2, especially a way to show that it's equal to something very large. However, our work complicates the picture. We show that the same technique also works for QMA plus. So there are constants C and S where QMA plus is equal to nx. Now on the one hand, QMA plus is equal to QMA, which is inside P space and x, and on the other hand, it's equal to nx. So unless there's a really big collapse in complexity classes, then QMA plus cannot have gap amplification. So here I have a picture, of the C over S ratio. On one side it's going to be equal to QMA, on the other side will be equal to nx. And so assuming that these classes are not equal, which is a very common, very widely believed assumption in computer science, there is no gap amplification of QMA plus. Now, how should we interpret these results? I've introduced QMA and QMA2 and also their plus versions. And you might say, okay, maybe the plus is what's making it really powerful. Maybe the 2 isn't that powerful. But I think if you're optimistic about this plus technique, you should know that any technique that amplifies the promise gap of QMA2 plus cannot work for QMA plus, because it would lead to this really strange breakdown in complexity classes. So I'll mention some key ideas in the paper. I won't have time to get into all the main approaches, but you can see my assignments talk for that. First, we're going to put NP in QMA plus with a logarithmic size qubit proof. So we're going to take an NP hard problem, let's say a CSP, a constraint satisfaction problem, And we're going to appeal to the PCP theorem to say that the problem has a constant size promise gap. And this will be important. Then what the verifier will do is it'll use the plus guarantee of the witness to demand a certain kind of property of the witness. So because the verifier knows that the witness has non-negative amplitudes, they can ask for something more. They can do a property test for something more. And if the witness has the property, they can proceed with the verification. And if it doesn't have the property, they reject. So suppose we have this rigid property. Then the verifier can check the constraints in the witness, again using PCP theorem. We can make sure that we succeed with a constant size promise gap. Lastly, we can scale this entire argument to put nx in QMA plus. Since everything was small, the logarithmic size qubit witness becomes polynomial sized, and the NP hard problem becomes nx hard. We just have to be a little bit careful about succinct representations of exponentially sized objects. Now, in general, I should say this is the same argument, the same flow that comes up in the Geronimo and Wu paper, but we make several adjustments to make sure that we only use one copy of the witness, where they use multiple copies. And I'll try to mention the main idea, which I think makes QMA plus, the plus thing, so powerful. And I think it boils down to amplitude and interference. And the intuition, at least I have, is that non-negative amplitudes kind of take the interference out of the quantum state. You know, you can no longer have things cancel out. On the left, we have two signals that kind of destructively interfere to zero. But on the right, we have two non-negative amplitude signals that can only constructively interfere. And I think this non-negative amplitudes condition is kind of giving you more info about the signal that might be kind of non-physical. In particular, if you have a state with non-negative amplitudes, then its overlap with the uniform superposition is proportional to the one norm of the state. And so in the protocol that we construct, the verifier is using a projector to the uniform superposition to demand certain properties about the quantum witness. You can kind of force the quantum witness to be a uniform superposition over kind of variable value pairs, or at least constraint value pairs. And you can see our paper or the Simon's talk for more information about this. But I think in general, the non-negative amplitudes are kind of taking out something physical and making it more like a exponentially compressed data structure, which is how QMA Plus is able to verify exponential time computation. Now, in general, these promise symmetric classes, where we're changing both the yes and the no case of QMA, can be very powerful. But it should be clear that the promise gap sometimes really matters. You know, here QMA plus interpolates from QMA all the way up to NX. And the difference only is in constants. The C and S only change, they're just different constants. And so one natural question is this: is there some kind of critical point? You know, is there a phase transition in constants where maybe on one side it's NX, but on the other side it's QMA? And the same thing might also be true for QMA2+. But you might also be more optimistic about this plus direction. You might say, hey, I actually think QMA2 is equal to NX. And I think this plus QMA2+ is a great way to try to show it. If you could show promise gap amplification of QMA2+, then you'd resolve the question. And in light of that, in light of our work, you should know that whatever amplification technique you're going to try to build, it can't work for QMA+. So it's going to have to involve this unentanglement, the separability condition, in a really crucial way. And these techniques are going to be more challenging. They might be harder to find too. And so the big question in this direction is, what does QMA2 plus have that QMA plus doesn't? And this might help us understand more about entanglement, at least from a complexity theorist point of view. So thanks for listening. University of Chicago, and have a nice day.